Hello everyone, I Dr. Tarkeshwari Verma here the present lecture on topic Fermi level and Fermi Dirac distribution function. That topic comes under the course Fundamental of Electronics Engineering. The content of the lectures are band theory of the solids, valence band and conduction band, forbidden energy gap, classification of solid, Fermi level and Fermi energy, effect of the temperature on Fermi level, Fermi Dirac distribution function. Before the discussing about Fermi level and Fermi Dirac distribution function, let's have quick recap about some basic concept of band theory of solids. The presented image shows every atom is associated with its own energy level. When two atoms are placed apart them, they do not interact it. Two atoms close together causes particular energy level to split into two energy levels. Band theory of solids explain how energy bands are formed within a solid. Valence band. The band formed by series of energy level containing valence electron is called valence band. It may be completely filled or partially filled with electrons. Conduction band. The band formed by energy values of free electron that have broken their covalent bond is called the conduction band. Conduction band is next permitted energy band. It may be empty or partially filled with electrons. Forbidden energy gap. The energy gap between the valence band and conduction band is called forbidden energy gap or forbidden band or band gap. This band is formed by series of non-permitted energy levels above the top of the valence band and below the bottom of conduction band. Energy gap is denoted by Eg and its amount of the energy supplied to excite the electrons from valence band and conduction band. It is measured in electron volt. Now we discuss the classification of the solid on the basis of energy band diagram. First is the insulator, second is the conductor and third one is the semiconductor. Now we will start with the insulator. Here the picture says insulator have two energy levels. One is the conduction band and second is the valence band. Here the insulator have two energy bands, first conduction band and second is the valence band. Between the both bands there are the maximum gap. Is that gap known as the energy gap. Material which do not conduct current is called insulator. Conduction band and valence band separated with large energy gap which is greater than 5 electron volt. Second one is the conductor. Here the image says conduction band and valence band are overlapped. There are no space for the energy gap. Material which conduct current is called conductor. As valence band overlap the conduction band and energy gap is the 0. If electric field is applied to this solid, electrons in a valence band have easy access to move conduction band and current flows through material. Third is the semiconductor. Semiconductor. The present picture shows the diagram of the semiconductor material. There are the conduction band and valence band. Material which have conductivity lies between the insulator and conductor are called the semiconductor. Energy gap is the small and it is of the above 1 electron volt. Types of the semiconductor. There are the two types of the semiconductor. First is the intrinsic semiconductor and second one is the extrinsic semiconductor. Chemically pure semiconductor is called intrinsic semiconductor. Extrinsic semiconductor, that semiconductor doped with some external impurity are called extrinsic semiconductor. We use new word doping. So what is the doping? Doping is a process of adding impurity into extrinsic semiconductor, intrinsic semiconductor. That means we have pure kind of semiconductor. We can't add any impurity. In this image we can see we are using pure silicon material. Another image shows that conduction band and valence band and empty space between them known as the energy gap. That value is the 1.1 electron volt. Extrinsic semiconductor. When we mix or add to impurity in a semiconductor material, that type of the material known as the extrinsic semiconductor. There are two type of the extrinsic semiconductor, N type and P type. N type of semiconductor, semiconductors doped with the pentavalent impurity just like arsenic are called N type of semiconductor. As the pentavalent impurity atom denote free electron is called the donor impurity. Donor impurities create an energy level close to the conduction band and represented by E D. P type of the semiconductor. P type of the semiconductor doped with the trivalent impurity are called P type of the semiconductor. As trivalent impurity accept free electron, so we call them acceptor. Acceptor impurities create discrete energy level close to the valence band and represented by EA. Concept of the holes. Holes nothing but is the absence of the electrons. This is the deficiency or of the negative charge can be treated as the positive charge. Holes are positive charge carriers. Movement of the electrons from nearby sites gives rise to movement of holes in a opposite direction. Fermi level and Fermi energy. Fermi level for the conductor material, the highest occupied energy level at 0 Kelvin is called Fermi level and the energy corresponding to it is called Fermi energy. For semiconductors, Fermi level is the reference energy level and it is correspond to the center of the gravity of conduction electron and valence hole. Fermi level in intrinsic semiconductor. In an image we can see conduction band and valence band and Fermi level lies between them. At a 0 temperature, if 0 Kelvin, the number of electron in conduction band equal to the number of holes in a valence band. That means N E is equal to N H is equal to N I. That means the number of the electrons are equal to the number of holes and total concentration of the charge carriers are equals. The Fermi levels lies in the middle of the band gap. If the temperature is not equal to 0 Kelvin, the depends upon the effective mass of electrons and hole. The equation presented by EF is equal to Eg divided by 2 plus 3 by 4 K T log over Mn effective mass of is divided by Mh. Fermi level in a p type of the semiconductor. The number of the holes in a valence band are greater than number of the electron in conduction band. So, the Fermi level shift toward the valence band. With the temperature, Fermi level shift toward the energy gap toward the Eg. Fermi level in a n type of the semiconductor. The image shows the number of the electron in a conduction band are greater than number of the holes in a valence band. So, the Fermi level shift toward the conduction band. With the temperature, Fermi level shift toward the EFI. This is the effect of the temperature on Fermi function. The above diagram represent variation of Fe as a function of temperature. All the curve passes through the crossover the point C correspond to the Fe is equal to 1 by 2. Now, let us start with our main topic, Fermi Dirac distribution. Two key scientists behind the development of the Fermi Dirac statistics. First is the Enrico Fermi and P.A.M. Dirac. Carrier concentration. We start about that topic, we should know about what is the carrier concentration. Current is the rate of which charge flows. The charge carriers in a semiconductor are electrons and holes. Determine the electrical properties and analyze device behavior. We often need to know the carrier concentration. That means number of the electrons and holes per centimeter cube of the material. For heavily doped intrinsic semiconductor, we can express the mathematical form these are presented. However, we do not know anything about the majority carriers concentration, nor we know about the temperature dependent of the carriers. In this section, we wish to determine the concentration of the electrons and holes in the conduction and valence band. This is the mathematical representation of the carrier concentration. The carrier concentration, equilibrium, electrons and hole concentration. Calculate the number of electron in a conduction band and holes in a valence band. We must know how many states are available, what is the probability of occupancy. We thus introduce GE, DE, density of states available for occupancy in an energy range DE. Electron distribution. The distribution with respect to the energy of electrons in a conduction band is given by density of allowed quantum states times the probability Fe, that is the electron occupied a state. which is mathematically represented by this, where Fe is the Fermi Dirac probability function and Ge is the density of quantum states in a conduction band. Now, hole distribution. The distribution with respect to the empty or hole in the band given by density of the allowed quantum states Ge times the probability is 1 minus Fe, that states not occupied by the electron. Both Ge and Fe are the terms of per unit volume or per unit energy. Fermi Dirac distribution. Fermi Dirac distribution function, which provide the probability of occupancy of the energy levels by electrons, is based on following premises. First, particle, that means any electron, are indistinguishable and only one particle is allowed in each quantum state. At absolute zero temperature, the energy level are all filled up to the maximum level called the Fermi level. Beyond the Fermi level, all states are empty. At higher temperature, there is the gradual transition between the completely filled state and the completely empty state. Mathematically, Fermi Dirac distribution function is represented by that and give the probability that an available state at the energy will be occupied by electron at absolute temperature T. The quality E is called the Fermi level and K is the Boltzmann constant. They have some value. This is the mathematical representation of the Fermi Dirac distribution function. F E is equal to 1 by 1 plus e raised to the power e minus EVF is equal to 1. If there are the some term and condition apply, then after we get the total value of Fe, that means the density of state is become 1. Consider this is the mathematical representation of Fermi Dirac distribution function. Consider there are the situation where T is equal to 0 Kelvin, then if E less than EF, then we get the value of Fe is equal to 1. When E is greater than EF, then Fe, density of the state, is we have 0. Thus, for the T is equal to 0 Kelvin, for the energies E less than EF, all states are filled. For the energy E greater than EF, all states are empty. Consider next situation, T is greater than 0 Kelvin, then that condition E is equal to EF. Then the density of state we have 1 by 2. Thus, an energy state at the Fermi level has probability of 1 by 2 of the being occupied by the electron. In general, for the temperature T greater than 0, there is the non-zero probability that some energy state above E will be occupied by electrons and some energy states below EF will be empty. This is the Fermi Dirac distribution function. Here we can see the for the conductor and semiconductor. The highest occupied energy level at 0 Kelvin is the called Fermi level, and energy correspond to its called the Fermi energy. For the semiconductor, Fermi level is reference energy level and it corresponds to the center of the gravity of the conduction electron and valence hole. The Fermi Dirac distribution is the important for understanding the behavior of electron in a solid electron band structure and has various applications, some of which include: first, metallic conductivity. The Fermi Dirac distribution is the used to calculate the electron density and probability of electron occupation in different energy states in a metal, which in turn helps to understand the electrical conductivity and behavior under different temperatures. Second, semiconductor physics. In the semiconductor materials, the Fermi Dirac distribution is employed to study carrier concentration of electron and hole at different temperatures, aiding the design and analysis of electronic devices like transistor and diodes. Third is the thermonic emission. The distribution is used to model the emission of electron from hot surface, that means the thermonic emission, and calculate the current flow in a thermonic devices like thermonic power converters. Calculate the current flow in thermionic devices like thermionic power conversion or converters. Photovoltaic devices. In solar cell, the Fermi Dirac distribution is utilized to describe the probability of electron occupying the energy state within the material, affecting the performance in converting sunlight to electricity. Next one is the Fermi level position. The distribution helps to determine the position of Fermi levels in a material concerning the conduction and valence band, which is crucial for understanding charge transport phenomena. Next one is the electron transport in a nanoscale devices. This distribution function we can use to analyze electron transport in a nanoscale devices like quantum dots and nanowires, where quantum effect become significant. Fermi Dirac distribution helps to understand where Fermi energy level are established in our semiconductor devices and conductors and insulator materials, that with help of that we know the exact conductivity of any semiconductor, conductors and insulator materials. We can easily find out and calculate. So, overall the Fermi Dirac distribution is the very important tool for understanding the behavior of fermions, particularly electrons, in various physical systems ranging from solid and semiconductor, advanced electronic and photovoltaic devices. Thank you.